Hello everybody, this is Dr. Tajdarul Hassan Syed. I am an associate professor in the Department of Applied Geology, IIT ISM Dhanbad. In this module, I am going to present some of the very basic concepts of hydrogeology or the study of groundwater. So here I am going to concentrate mostly on the saturated portion of the subsurface. So as we have talked earlier that the subsurface is consisting of different unconsolidated and consolidated materials. Some portion just below the surface is unsaturated with respect to water that we call as the unsaturated zone, and the portion which is saturated with respect to water is known as the saturated zone or the phreatic zone, and the water that exists there is known as groundwater. So what we will discuss here today is a very fundamental aspect of the movement of groundwater. So if we see that we have a groundwater system, so if we consider this as the surface of the earth, and here I draw a line which basically differentiates between the unsaturated zone and the saturated zone of the subsurface. So we call this as the unsaturated zone, and this is the saturated zone. So the water that is existing here is known as groundwater, as I have talked earlier. So there is a lateral movement from groundwater from one place to the other. So groundwater can move from one place to the other. So we're going to discuss what are the principles behind it. Now the equation, which is very famously known as Darcy's law, quantifies actually the volume of water that is flowing from one point in the aquifer system to the other point in the aquifer system. If I can write very briefly what is Darcy's law. Darcy's law basically states that the volume of groundwater that is flowing per unit time is equals to the hydraulic conductivity, which is represented by K. It is known as the hydraulic conductivity. And this A is the area of cross section of the aquifer. So this is basically the area of cross section of the aquifer, and this term is basically known as the hydraulic gradient. So the thing is that what this term says is the volume of water flowing is given by KADHDL. So the question is, when the water is flowing from one point to the other, what is the driving force? And in this equation, we can see that the hydraulic gradient is the driving force which makes the water move from one place to the other. But before we understand what is hydraulic gradient, we have to understand what is this term H, which is we are defining as the hydraulic head, which will be the focus, major focus of this module. Now, when we are talking about the hydraulic head, we are saying that this is the energy that is making the water move from one place to the other. So in order to understand how this hydraulic head is representing energy, we have to understand what is a fluid potential and how the hydraulic head is acting as a fluid potential. So we are going to understand and derive how the hydraulic head is actually represented in terms of energy. So we can see what is a fluid potential. First of all, what is a fluid potential is basically defined as it's a physical quantity that can be measured, and the flow of that fluid is going to take place from higher fluid potential to that of lower fluid potential. Just as an analogous case, we can say that electricity moves from higher voltage to lower voltage. So voltage is basically sort of a potential. Similarly, we can see heat transfers from higher temperature to lower temperature. So temperature is kind of a potential. And because groundwater also moves from higher hydraulic head to lower hydraulic head, we can say that the hydraulic head is analogous to a fluid potential. So what we are trying to say here is that the hydraulic gradient is the potential gradient. That means the difference in the two hydraulic heads is what is quantifying the volume of water that is going to flow from one point of the aquifer towards the other point of the aquifer. So the total energy that is required for the movement of groundwater from one point to the other has three different components. One is basically the potential energy, which is basically given by the mgz, that means the energy by virtue of its elevation. Another is the kinetic energy. This is the energy required for the mass to be accelerated from the static state to a particular velocity v. So this is given by half mv squared. And the third is the pressure potential energy. So this is the energy required to move the water from pressure of P0 to a certain P. So basically what it stands for, in other words, we can say that the pressure potential energy is basically the pressure exerted by the surrounding fluid. So here we represent this as pressure. Now how is pressure in terms of why we are calling the pressure as the pressure potential energy is, if you look at it, pressure is defined by force per unit area. So force is given by the units Newton and area by meter square. So now if I multiply length here up and down, which basically cancels out, so we can say that this is equals to Newton meter per meter cube. So Newton meter is basically, we can say this, the pressure is represented as potential energy per unit volume. So pressure, as we can see, is basically potential energy per unit volume. So these are the components of the total mechanical energy that is required for the movement of groundwater from one point in the aquifer system to the other point in the aquifer system. So here what we are saying is that if I have two different points which are located at two different elevations, the potential energy required is given by mgz, which is the difference in the elevations. If the volume at the point, the velocity is 0 and we are accelerating it to v, the kinetic energy is half mv squared. And then we, if there is a difference in the pressures of the two different points, we are saying that the energy required will be known as the pressure potential energy. So now if I sum up all these three energy terms and I say that what is the total potential energy per unit volume. So now I am trying to represent the equation for the total mechanical energy per unit volume. So I'm going to write the total energy as ET, and because it is per unit volume, I am adding another subscript which is V because it's per unit volume. So I can say that this is mgz divided by volume plus half mv square divided by volume plus P. Why P I'm leaving it? Because P is already potential energy per unit volume. So now if I see here, I can simplify this equation saying that m mass divided by volume is basically density. So I can represent that by rho, which is the standard symbol for density. And then I am writing g, which is the gravitational acceleration, h is the altitude or elevation, plus half again rho v square. Why rho? Because mass divided by volume is density, plus I am writing P, which is basically the total potential energy per unit volume. Now from this equation I want to write the equation for total mechanical energy per unit mass. Okay, so what I'm saying is, as we know that for a unit volume of an object, the mass is basically equals to the density. Okay, so what I'm saying is that the equation I am dividing by rho. Why? The reason is that because we know that density is equals to mass by volume, and if volume is 1, so rho becomes equals to m. So when I'm saying that this is the total mechanical energy per unit mass, I am dividing it by rho, and then for the entire equation I am dividing by rho plus pressure divided by rho. So this is the equation of the total mechanical energy per unit mass. So if I simplify it, I see it comes to Gz plus half V square plus P by rho. So what is this? This is the total mechanical energy per unit mass. This is also the definition of a fluid potential. So fluid potential again can be defined as the total mechanical energy per unit mass. So this entire term we can say is the equation for the total mechanical energy per unit mass or the fluid potential. Now what I want to derive from this term is the total mechanical energy per unit weight. So in order to do that, what I am doing is I am dividing that equation by the gravitational acceleration. So half by 2g plus p by rho g. So here what I am representing here is that this is the total mechanical energy per unit weight. So if I simplify it, it simply comes to v square by 2g plus p by rho g. Okay. So here if we see that the unit of all these three terms are in meters. So what we see here is this is pressure. Pressure is actually we know is given by rho g h. Basically this is the hydrostatic pressure. This is the pressure exerted by a column of height of water h. So we can see here that all these terms have a unit of meters, and this entire term is what is known as the hydraulic head of an aquifer. So what I'm saying here is that this has three different terms. As we can see, one is the elevation term, another is the velocity term, another is the pressure term. So if I am defining so at two different places, so what I'm saying is that how do you define a hydraulic head? Hydraulic head gives the status of the total energy of a point at an elevation z, which has a velocity of v and is acted upon by a pressure of p. So if I have two different points, I will have the two different values of z, v and p, which is the pressure exerted on the particular point in the aquifer system. So here I can say, if I take into consideration an aquifer, say for example I have an aquifer, say this is the aquifer system, and I have subsurface, say for example I have two wells here and I have another well here, and the water that is standing here in this well is somewhere here, and the water that is standing here in this well is somewhere. So if I consider this as point 1, this as point 2, then I can write down that the hydraulic head H1 at this particular point of the well is given by Z1 plus V1 square by 2G plus P1 by rho G. And for the point 2, which is another point in the same aquifer, H2 is equals to Z2 plus V2 square by G plus P2 rho G. So you can see here that the water that is going to flow from point 1 to point 2 of the aquifer is dependent on the difference in the energy that is present in point 1, which is represented by H1, and the difference with whom? The difference with point 2, which is again defined by the elevations and the velocity and the pressure at these two particular points. Now the thing is that how is these two things measured? The thing is that whenever we are measuring the elevation, it is with respect to a universal datum, and which we generally consider as the global mean sea level. So here we can say that this is Z1, which is the elevation. This is Z2, and here, as I said, P1 and P2. Why? Because P1 and P2 are the pressure exerted by the water column at these 2 points. What is the height of the water column? The height of the water column is, say, HP1 in this case, and in this case it is HP2. So what we are saying is that the 2 points have differences in the pressure which is exerted by the column, the velocity, and also the elevation with respect to the mean sea level. Now what often happens is that in case of groundwater flow, the velocity is generally very, very small. So often what we tend to do is that the velocity, if it's a small term, as we know, and if we square it up, that even becomes smaller. So generally what happens is that these velocity terms are actually neglected. So if we neglect them, we can see that we can rewrite the equation as Z1 plus P1 by rho g, or we can say equals to Z1 plus HP1. In the same case, we can write for Z2, which is the point, for point 2, we can write Z2 plus P2 by rho g, which is equals to Z2 plus HP2. So here, finally, what we see here, that the hydraulic head of 2 points within an aquifer is represented by 2 terms. One is by the elevation, another is by the pressure. So the hydraulic head, we can sum it up as like this: the hydraulic head has 2 components. One is known as the elevation head, another is known as the pressure head. But this is very important to understand that the movement of groundwater is not dependent on the individual components only. It is only dependent on the sum of these 2 components. So we can see that the hydraulic head is basically the summation of the pressure head and the elevation head. And as I was talking about, that the movement of groundwater is not dependent either just on the elevation head or just on the pressure head. It depends upon the sum total of the 2. So if I rewrite the equation that hydraulic head is equals to elevation head plus the pressure head, now I'm going to, just to better illustrate, I'm going to draw 2 different conditions. Okay. Now here in this first case I'm saying that I have an aquifer like this, and I have here the elevation is at point 1 is, say, let's say this is point 1 and this is point 2, and at point 1 it has an elevation. This is the datum over with respect to which I am measuring the elevation, and I have the pressure head of HP1. And in point 2, I see I have an elevation of Z2 and the pressure head, let me say pressure head of HP2. So in this case, I'm saying that I have an aquifer which is tilted in this direction. And in this case, what are the conditions? I see that Z1 is actually less than Z2 and HP1 is greater than HP2. Now the thing is, in spite of being tilted in this direction, the water is going to flow from point 1 to point 2 in spite of the differences in the elevation. So it seems like the water is moving uphill. The reason is that if I take the sum total, which is H1, that is the hydraulic head of point 1, and I take the sum total of the point 2 hydraulic head, because H1 is greater than H2, the water is going to move sort of up the gradient. Okay, so this is just to show that even though often people have the concept that because water cannot move up the gradient, the thing is here we are seeing that in spite of the fact that the gradient is the water is moving sort of up the gradient. Okay, now just to illustrate more, I take another case, okay, in which I'm saying that, again, this is my datum, and I'm saying that the aquifer is absolutely horizontal. Okay, that means I'm saying that this is point 1 and this is point 2. Here I'm saying this is Z1, this is Z2. However, the hydraulic head, the pressure head, this is HP1 and this is HP2. Again, as we see, if we take the sum total of the two components, we are seeing that if this is H1 and sum total of this is H2, since H1 is greater than H2, water is going to move from point 1 to point 2, in spite of the fact that Z1 is equals to Z2, but we have to see that HP1 is greater than HP2, which makes that the total hydraulic head of point 1 is greater than the hydraulic head of point 2. That's why the water is going to move from point 1 and point 2. So we can draw several cases like this in order to understand that it is not just the pressure head which controls the movement of water, neither is the elevation head the sole factor which controls the movement of water from one place to the other. So the hydraulic head is the most important quantity here, and which is basically the summation, the addition of the hydraulic head and the pressure head that controls the volume of water that is moving from one place to the other. So just to summarize this module, I would like to say that the groundwater is a component which moves within itself from one place to the other. But what controls the movement, or which drives, the force which drives the movement of water, is basically the hydraulic head. And how much of movement is going to take place is basically given by what is known as the hydraulic gradient. That means what is the rate at which the hydraulic head is changing from one place to the other. So the direction of the flow is given by obviously from higher hydraulic head to lower hydraulic head, and the volume of flow, or the amount of movement that is going to take place, is, we have to remember, it is given by what is known as the hydraulic gradient, or the change in the gradient that is taking place between the 2 points which are separated by certain distance. So this hydraulic head, as we have to understand, is a very basic principle, and these hydraulic head measurements are immensely useful for ascertaining certain hydrogeologic properties as well. So thank you very much for listening and for paying attention. Thank you very much.